Hi everyone. In today's video, we will discuss a few more applications of Gauss theorem. In the video I posted 1 week back, I have explained Gauss theorem, the uses of Gauss theorem for what all practical purposes we can apply the theorem. We also discussed a few examples and found the electric field by applying the theorem. So today we will extend our discussions a little further. We will try to find the electric field due to a plane sheet of charge, then the electric field due to a conducting plate. We place two charged plane sheets close to each other and inspect the electric field in the region surrounding these sheets. And finally, towards the end, we will solve a problem from V.K. Mehta's book, Concepts of Physics. So that is how we are going to proceed in this class. Okay, now let us apply the theorem to the case of an infinite plane sheet of charge, which is charged with a uniform charge density sigma, positive charge density sigma. So as we have discussed in the previous class, we will construct a Gaussian surface which is a cylinder, and we will assume that the area enclosed by the Gaussian surface, the area of the sheet that is enclosed within the Gaussian surface is S. Now as you look at the diagram, you can see that on both the curved surfaces, the faces of the cylinder, the electric field vector and the area vector are parallel to each other, and therefore cos theta is 1, because theta is 0. So over these two flat surfaces, the flux is maximum. Now look at the curved surface of the cylinder. Here, if we mark the direction of the area vector, it will be along this direction. Take a small area here, and if you look at the area vector, it is pointing upward, and the electric field vector is along the axis of the cylinder. Therefore, the angle between the two is 90 degrees, and the flux over the curved surface everywhere is 0. So we have two surfaces over which the flux is maximum. So according to Gauss theorem, so you can write Gauss theorem as integral E dot ds equal to Q net divided by epsilon 0. So now, as we have seen, the net flux through the faces will be 2 into Es. Now why 2 into Es? Because integral E dot ds is E ds cos theta is 1. So integral E ds, take E outside, integral ds is A, which is the area of the two faces of the cylinder, and there are two faces. Now you have a plane sheet of charge. So when you charge such a sheet, the same charge will appear on both the surfaces. So you have two surfaces over which the charge is the same. So the net flux will be 2 Es. This should be equal to net charge enclosed by the Gaussian surface divided by epsilon 0. Now what is the net charge enclosed by the surface? As I told you, the area of the Gaussian surface that is enclosed by the area of the sheet that is enclosed by the cylinder Gaussian surface is S. Therefore, this will be equal to sigma into S divided by epsilon 0. The net charge is sigma S. And upon simplification, we will get this as E is equal to sigma divided by 2 epsilon 0. So that is the result for a plane sheet of charge. So for a plane sheet of charge, the electric field will be sigma by 2 epsilon 0. Now, as you can see from this diagram, from this result, the electric field is independent of the distance. So in this final answer, you will not find the distance to the point where the electric field is to be evaluated. So for points which are not very far away, the electric field remains more or less constant, and it is given by E is equal to sigma by 2 epsilon 0. Clear? Now let us discuss the electric field due to a conducting plate. Now for an insulating sheet, for a plane sheet of charge, we have obtained this result sigma by 2 epsilon 0. So in our example, we have given positive charge to the sheet, and the electric field was directed away from the sheet because the charge density was positive. Now the difference between a sheet and a plate or conducting plate is that in the case of sheet, as I told you, the same charge will appear on both the surfaces, whereas in the case of this plate, the two sides will hold separate charges. So you have a charge Q here and same charge Q here. So the two sides of the plate can hold charges separately. Now the electric field due to this can be obtained by using Gauss theorem or by the principle of superposition, which is very easy. Now if you consider a point here, the electric field due to the charges on this side, which is 1, can be considered as sigma by 2 epsilon 0, which we have derived. And the direction of the electric field at this point due to the charges present on the side 1 will be E1, and that will be directed in this along this diagonal. And the electric field at the same point, let us call this point as P, due to the charges on the side 2 will also be, or that can also be written as E2. That can be written as E2 and the direction will be the same. Now the two sides, since the two sides are holding charges of the same magnitude or the charge density is the same, therefore the resultant electric field at the point P will be equal to E1 plus E2, which is equal to sigma by 2 epsilon 0 plus sigma by 2 epsilon 0, which will give you sigma by epsilon 0 as your final result. So this is the electric field due to a conducting plate, which is twice the electric field due to a sheet. Remember, the difference between these two results lies in the fact that in the case of an insulating sheet or a plain sheet of charge, same charge will appear on both the surfaces, whereas in the case of the conducting plate, the two sides can hold charges separately, and that is why if you multiply this with 2, you will get this. So the electric field due to a conducting plate is twice the electric field due to a plain sheet of charge. Now we have derived the result for the point P, or we have calculated the net electric field at P, which was to the left of the sheet. Now if you consider another point P to the right of the sheet, you will get the same answer. The calculation is the same. You can evaluate or you can find out the resultant electric field at another point P or Q on the right side of the sheet by the same principle, which is the principle of superposition. You will end up with the sigma by epsilon 0. The difference is here the electric field will be directed towards the right, and here it was directed towards the left. Now we will try to find out the electric field at any point inside this conducting plate. So our next step will be to find out the resultant field at any point which is situated inside the conducting plate. Now you see the diagram. The point P is located inside the conducting plate. We want to find the resultant electric field at P due to the charges appearing on the sides 1 and 2. Now you know that these electric fields will be equal in magnitude and opposite in direction, because we have earlier seen that when the point P was to the left of the sheet conducting plate, the electric field had a direction which was towards the left. Now when the same point P came to the right, the electric field at P was towards the right, having the same magnitude. So when the point P comes to the inside of the conducting plate, the resultant field at P should be E1 minus E2, which is sigma by 2 epsilon 0 minus sigma by 2 epsilon 0, which is 0. So we have seen that this is a very important result. We have seen that there is no electric field inside the conducting plate. Now let us find out the electric field due to two plate sheets of charge which are having surface charge density, positive surface charge density sigma 1 and sigma 2. We have three regions 1, 2, 3 and also 3 points A, B and C. The region 1 is to the left of both the sheets, region 3 to the right of both the sheets, and region 2 is in between the two sheets. Now we will also assume that the fields to the left of the sheets are negative and the fields to the right of the sheets are positive. So now with these ideas in mind, let us first evaluate the resultant electric field at A. Now the resultant electric field at A will be, as you have seen from the diagram, the point A is situated to the left of both the sheets, having charge density sigma 1 and sigma 2, and we have assumed that the electric field at any point to the left of the sheets is negative. So this will be minus sigma 1 by 2 epsilon 0 minus sigma 2 divided by 2 epsilon 0, because both the electric fields are negative according to our convention. and for the region B, this will be sigma 1 by 2 epsilon 0 and minus sigma 2 by 2 epsilon 0. And what about for the region C? For the region C, it will be sigma 1 by 2 epsilon 0 plus sigma 2 by 2 epsilon 0. So those are our results for the region A, B and C respectively. Now we will deal with a special case. Suppose sigma 1 equal to sigma and sigma 2 equal to minus sigma. The plates are charged with equal and opposite charge densities. We have given charges of equal magnitude but opposite sign to the plates. Then what will happen? Immediately you will find that both A and C become 0. So if you put a sigma 1 equal to sigma and sigma 2 equal to minus sigma, both EA and EC will become 0. And what about EB? Then EB will be equal to sigma 1 by 2 sigma by 2 epsilon 0 plus sigma by 2 epsilon 0, which is again sigma by epsilon 0. This is a very interesting result, because when you give charges to the plates in such a way that the charge densities or charges are equal in magnitude and opposite in sign, and electric field will exist only in the region between the two sheets. This is a very important result in the study of capacitors. So that is our another application, when the plates are having charge densities which are equal in magnitude and opposite in sign. Now we are going to prove a very important result by using Gauss theorem. So we have two conducting plates which are given charges Q1 and Q2. Now we want to get a relationship between the charges appearing on the facing sides. Let us assume that they are Q1 and Q2. So I want to find a relationship between Q1 and Q2. To get that, I have drawn a Gaussian surface, constructed a Gaussian surface like this. Now let us look at the electric field and the flux through each part of this Gaussian surface. These two parts are lying within the conductor where the electric field is 0. So flux through these surfaces, these two sides is 0, because those two are inside the conducting body where the electric field is 0. Now look at these two sides. The electric field is parallel to the side, and if you draw an area vector, the area vector will be along this direction and the electric field is along this direction, which means that the angle between the two is 90 and again the flux is 0. So we find that there is no flux either on these two sides or on these two sides. So the net charge enclosed by the Gaussian surface should be 0 according to Gauss theorem, because the net flux is 0. Now we have assumed that we have marked the charges on the facing sides as Q1 and Q2. Since there is no net charge enclosed by the Gaussian surface, Q1 plus Q2 should be equal to 0 or Q1 equal to minus Q2. That is a very important result. So the facing sides will always have charges which are equal in magnitude and opposite in sign. Now we will extend our treatment a little further. So now again we have two metallic plates of charges Q1 and Q2. We want to find the charges appearing on both the surface of the plates, that is on 1 and 2 on this plate and 3 and 4 on this plate. We have already result that the facing surfaces of the sheets will have always charges which are equal and opposite. So we assume that the charge appearing on the surface 2 is Q. Then this should be minus Q. That result we have obtained a little earlier. Now by the conservation of charge, here you must have Q1 minus Q, and here it should be Q2 plus Q according to the conservation of charge. Now we will take a point P here. Since the point P is lying inside a conducting body, the net electric field at P should be 0. So by using the convention of the sign conventions that we have followed so far, we will write expressions for the net electric field at P due to the charges appearing on all the four surfaces of both the sheets. So the resultant electric field at P will be equal to Q1 minus Q divided by 2A epsilon 0 minus Q divided by 2a epsilon 0 plus q divided by 2a epsilon 0 minus of q2 plus q divided by 2a epsilon 0, and this should be equal to 0 because the point P is inside a conducting body. Let us simplify this. So we will get q1 minus q plus q minus q2 minus q equal to 0. So this will be plus q and minus q get cancelled. q1 minus q2 equal to 2q, and therefore q is equal to q1 minus q2 divided by 2. This is a very important result. So now you have this charge as q1 minus q2 divided by 2. So what about this one? It will be minus of q1 minus q2 divided by 2. That is a very important result. So here you have q1 minus q2 by 2, and here we have minus of q1 minus q2 divided by 2. So now we have the charges appearing on the facing surfaces as q1 minus q2 by 2 and minus of q1 minus q2 by 2. Now what about the charges appearing on the outer surface of the two plates? If you substitute for q, then you will get this as q1 plus q2 divided by 2, and this one will also be q1 plus q2 divided by 2. So when you have two metallic plates which are charged like this, the facing surfaces of the two plates will get charges which are equal in magnitude and opposite in sign, and the two outer surfaces will get charges of equal magnitude. This is a very important result in electrostatics. So these two facing surfaces will get charges which are equal in magnitude and opposite in sign, and outer surfaces will get charges which are equal in magnitude. Clear? So now we have discussed the electric field due to a plane sheet of charge and conducting plate. We will solve a problem from V.K. Method's book Concept of Physics, Volume 2. And here you have three metallic plates which are having large surface areas, and they are the plate, the one is given a charge q, the plate 2 is neutral, and the plate 3 has a charge minus 2q. We want to find a charge that is appearing on the outer surface, outermost surface of the plate having a charge minus 2q. So we will call this as A, this one as B, and this one as C. So what is required is to find out the charge that will appear on the outer side of the plate C. So for this, again we will use the results that we have studied just now, and here we will do another technique, that is, instead of having three plates, we can reduce this to a case of two plates. This one does not carry any charge, so these three plates can be reduced to two plates, A and C, having charges q and minus 2q. Even if you have a charge on the plate B, the same type of reduction can be done. So whether you have three plates having charges, having different charges, you can reduce them to the case of two plates having some different type of charge. So you have to add the charges on these two and reduce it to a single plate. Here when we do that, we will end up with minus 2q because this is neutral. We will try to find the charges appearing on the outer surface of the plate C. I have redrawn the diagram, and instead of three plates, now we have only two plates. Plate A carrying a charge q and plate C carrying a charge minus 2q. Now I have written the charge appearing on the facing surface. We will call this as 1, 2, 3, 4. On the side 2, I have marked the charge appearing as q. Then, according to what we have seen just now, the charge appearing on the side 3 should be minus q. Now, if this is q, according to the conservation of charge, this should be minus q, and this should be minus 2q plus q. Now let us consider a point P here. Since the point P is inside a conductor, the net electric field at P should be 0. So now we will write the field at P as EP equal to, we will use the same sign conventions that we have been using so far. So EP will be equal to q minus q by 2a epsilon 0 minus q by 2 epsilon 0. Then this is plus q divided by 2a epsilon 0. And finally the last term minus of minus 2q plus q divided by 2a epsilon 0. Now we have to simplify this. This will be q minus q plus q plus 2q minus q equal to 0. Q and q get cancelled. So this will be 2q. This is 2q equal to 3q, or q equal to 3q by 2. So now we have this charge as q as 3q by 2. So quite clearly this will be minus 3q by 2. So I have replaced the q's with the charges which will appear on the sides 2 and 3. Now what about the charge appearing on the side 4? That is what is to be found out in the problem. So for that we will write it as minus 2q plus 3q by 2, which is equal to minus q by 2. So the charge appearing on this surface will be minus q by 2. And what is the charge appearing here? That is also minus q by 2. So the facing surfaces will have charges which are equal in magnitude and opposite in sign, and the two outer surfaces will have charges of equal magnitude.